me share my screen with you. We're gonna get started right away here. Hope you guys had a good long weekend and found some stuff to do. Um, on the long weekend, the weather was pretty nice. I went out golfing for the first time yesterday, and it was unreal. Um, I am incredibly tired and sore though from doing physical activity for the first time in like 3 months, is what it feels like. So my body is wrecked today. It was a long one. Went to Wildwood though, golfed pretty well. I was pretty happy with it. Um, I thought they were supposed to have like little blocks in the actual holes themselves, but they ended up just having like pool noodles in them. So like when you're putting, it just like bounces off the pool noodle and shoots out. It was kind of inconvenient, but it was what it was. I posted a video yesterday um, talking about Hess's heat law. You'll need to watch that video to do the assignment that I have posted this week, but we have actually concluded the heat unit. We flew through it. I'm not going to do a test for that unit. Yeah, I'm more concerned about getting through the content and doing like one weekly assignment each week and just kind of getting you the necessary skills to push us towards and get us to getting ready for Chem 30. And so that to me took doing a test took just less precedence. So we're actually transitioning now into waves. Um, this is now the physics part of physical science 20, and this physics part translates in some way to physics 30. Particularly when we talk about waves, it translates in specifically when we're talking about electric fields and magnetic fields. Um, so yeah, if physics 30 is something you're interested in, this is the part of the course that you'll enjoy the most. But basically what a wave is it's a transfer of energy in the form of a disturbance. Waves typically travel through a material substance known as the medium. That medium can be the air. That is technically a medium. However, not all waves require a medium in which to travel. So there's two different types of waves based on what they're moving through. There are electromagnetic and mechanical waves. Electromagnetic waves are waves that travel through a vacuum or an empty space, and they travel through at a speed of approximately 3.00 times 10 to the 8 meters per second. So that would be the speed of light, X-rays, and radio waves. And then there's also mechanical waves, and those require some sort of matter or medium to transport the wave. So we could think of that like a slinky, air particles, like a sound wave, or the ground, which would be like an earthquake wave. Those are kind of a couple examples. Um, a transverse wave. So the way we characterize and categorize waves is based on their shape that they have. The first way is a transverse wave, and this is where the particles in the medium move perpendicular to the direction that the wave is traveling. So, a slinky example would be the rings of the slinky move side to side, but the wave of energy moves forward. So, you have your little slinky, and it jumps down to the next little stair. It jumps down to the next little stair, and the energy just gets slowly transferred and transferred over time, and it keeps moving perpendicular to where the actual energy is traveling. So some really common examples would be radio waves, which when we have like our little radio towers, they send out a signal, and then it hits you while you're driving in your car, and you can listen to really terrible country music when you're driving around. So that's how radio waves travel, is they travel and they actually flow in the direction that they are actually traveling. Light waves are the same, heat waves are the same, and then electromagnetic waves. Those are all the same type of example of a transverse wave. The second is a longitudinal wave. The particles in the medium move parallel to the direction of the wave. So that would be like if we had a slinky, that would be like it shifting back and forth, moving just side to side. So the rings of the slinky move forward and backward, and the wave energy overall moves forward. So some common examples would be sound waves and then also pressure waves, which come in the form of earthquakes. So these are what a longitudinal and a transverse wave look like. Usually, when I think of the transverse wave, I think of that like workout where you grab onto the two ropes and you swing them up and down. That's kind of the best image I have of what a transverse wave looks like. And a longitudinal wave, usually what I think of is just like a spring. So if you pull back a spring, if you have like those door stop springs and you pull them straight back, they'll shoot in and then shoot straight out and just kind of bounce back and forth in that way. So that's kind of how I think of a longitudinal wave. Kind of the key idea here is the energy transport is both the same direction, but the way in which the source moves, so this part here, that's a really bad star, and this part here, those are the key differences. And then obviously the coil direction as well. The third type of wave here is a surface wave, and this is a combination of transverse and longitudinal waves at the surface of water. Kind of a way that you can think of that would be like tossing a pebble, or if you're skipping stones. That used to be something that me and my grandfather, we used to do that a lot. I love skipping rocks. There's a video on YouTube that exists, and it's about a guy who skips a rock. He's a professional rock skipper, which someone tell me how you get that job because that sounds insane. Um, but I think his record is 80 something times skipping a rock on water. And the theoretical, oh shoot, what is the theoretical number? I think theoretically you could skip a rock 180 times. I think it's roughly in that ballpark, which is pretty insane to think that you could generate that much force or spin. But yeah, so surface wave, kind of the way that these operate is like you skip a rock and it creates waves that spread out from the actual location where you're actually like skipping the rock. And then you create waves that go up and down, but you also create waves that just go out and come back in as well. So typically, if I was teaching in class, that would be the first lesson. Really, really straightforward. I chunked these two together. I felt it would be a more useful use of our time together to talk about the parts and components of waves as well. So, in terms of talking about a transverse wave, this is where we'll spend a lot of our time focused, is looking at these transverse waves because they are more common, but also because they're more useful and practical to us. So, some of the key terminology and key facts that you need to know is that the midline, this is kind of like equivalent to zero. So, it's like saying that it's at a 0 point. It's neither in the positive or negative direction. Anything above that is positive, anything below that is negative. So when we're looking at this particular graph, we have a bunch of different points. A, C, E, and G are all at the midline. Points B, that would be the very peak of the crest. And so all of this part here we would call the crest, but usually we're most concerned with this point B at the very top of it. And then a trough is in the opposite direction. It's in the negative side of said graph. And again, mostly we're concerned about that point D. Another thing that we're kind of interested about, and the reason that we are so concerned about these absolute peaks and the absolute lowest points, is we get something called the amplitude. And the amplitude is the measure from the midline to the top of the crest or to the bottom of the trough. And then the last kind of thing that we talk about is when we talk about wavelengths, we are mostly concerned about one hole crest and one hole trough. And we're going to see a symbol that looks like this over the course of time. This is the Greek symbol lambda, and that usually means wavelength. So if you see me draw this weird looking chair / L type weird letter, this is lambda, and I'm referring to the wavelength whenever I draw that symbol. But again, the idea that a wavelength is one hole crest and one hole trough. So actually for us, this would be from point A to point E. That is one whole wavelength. So traveling all the way up, down, and back to where we came from, and also traveling in the same direction that we came from. When you get to math, when you get to pre-calc, or if you take math foundations 30 from me or from Miss Neufeld, what you end up doing is you actually graph sine and cos graphs. A sine graph looks like this. It starts here, goes down, and it comes back up. And this represents, that represents, not 180, that represents 360 degrees, or it represents something called 2 pi. So if you've operated in radians before, that's what 2 pi looks like. And then a cos graph starts at the top, it comes down and comes back up. And same thing, this represents 360 degrees, or it represents 2 pi. And the idea of 2 pi is that it's like one complete circle or one complete wavelength. And so similarly with our little crest and trough, one whole crest plus one whole trough, that equals an entire wavelength. And usually we're concerned about the measurement from this point here up until this point here. We want to know what that distance is. So here's some just definitions of these different points. Crest is just a peak above the midline. Trough is a peak below the midline. The midline is the reference point for measuring a wave, and it's also an imaginary line down the middle of a wave. Amplitude is the maximum height of the crest measured from midpoint, and the strength of the wave. And then the wavelength is the length of one complete wave, one crest plus one trough. So again, that's all what we just talked about on that last slide. So one of the things I guess I didn't highlight is um, when we're looking at a wavelength, you can start wherever you want on the actual graph itself, and you will achieve a wavelength. If I wanted to start at point B, I certainly could, and I would finish my wavelength at point F then. The idea is, again, you want to see and you want to have an image that looks exactly like where you started with. So where it was coming from, where it's going, Cotton Eye Joe, so on and so forth. You could also start from C if you really wanted, and you would finish then at G, and that would be your entire wavelength. Again, the C and the G, they both look the exact same in terms of where the arrow was coming from and where it's now traveling. So that. Looking at a longitudinal wave, there are different things that we measure with a longitudinal wave. Kind of the main points are the compressions and the rarefactions. Those are the two concepts that we're most concerned with longitudinal waves. With longitudinal waves, a compression is a point on a medium through which a longitudinal wave is traveling where particles are most closely spaced. So compressions occur at A, C, and E. That's where all of the spring is the most compact. Rarefaction is where there is the widest space. So again, that would be at point B here, point D, and point F. And then the wavelength can always be determined by measuring the distance between any two corresponding points on the waves, two compressions or two rarefactions. So again, the idea is you want to go from one point and then go to the next point that looks identical. So if I wanted to measure a wavelength, I would go from A to C, and that would represent one wavelength. I could go from B to D. I could go from C to E, and those would all represent a wavelength. So transverse and longitudinal waves, they can be observed in two different manners. One is a wave pulse, so looking through a single disturbance that travels through a medium. Again, that would be kind of a graph or a wave that looks like this. Or we could look at a traveling wave, which is a continuous and consistent disturbance that travels through mediums. That would be us looking at a longer stretch of time looking at a wave. Some more terminology that we get to deal with. The period is the length of time it takes for a wave to go through one complete cycle or one complete wavelength. So the time that it takes for this to finish, the time that it takes for one wavelength to finish, is also known as the period, which is the amount of time. Um, Time per cycle is kind of the unit that we use. So the unit of this is time per cycle. The period has a time value, so it can be measured in seconds, minutes, hours. Again, it depends on really what you're measuring. Period is usually seconds. So generally, what we're saying is that like if something it can go to completion, it'll take 6 seconds for me to complete this. So, for example, when I'm estimating how long it will take me to mark some of your assignments, we'll say it takes me about 2 minutes per assignment to finish marking. I have 10 assignments. Well, I would know then this is going to take me 20 minutes to finish marking. So, we've used this kind of knowledge before, but now we're just changing it into a different vocabulary vernacular. One of the interesting things about period, or one of the interesting things that we can note, is you've probably seen things measured in frequencies before, or you've probably seen things measured in hertz before. This is hertz. And you can actually calculate the frequency, which is equal to hertz. It's also equal to this weird F symbol. Um, Frequency is just the inverse of the period. So if a period is seconds per cycle, a hertz is a cycles per second. And where that becomes um, a more valuable variable to operate with would be something like, so if you're listening to speakers, let's say that you're looking at into buying a pair of headphones, and you want to look at the speakers and see what kind of frequencies can they actually put out. If if we used periods instead of hertz, we would get smaller and smaller values the higher quality that the speaker was. Or better yet, let's think about cell phones. So most of your cell phone screens have a refresh rate of 60 hertz. That means 60 times per second your phone is refreshing what you're seeing. The new phones that are coming out recently, and I think the new iPhone is supposed to have an 120 hertz screen. So what that means is that 120 times per second, the iPhone screen is refreshing, which lets you, I don't know, observe your emojis or scroll through your really long texts faster and more efficiently. It looks more fluid, basically. And so if we were to use period instead of frequency, every time that like these screens were refreshing faster, the value would get smaller. So if it would be like 1 second, 1 second for 120 cycles. So you get a really, really small decimal value, which doesn't provide much insight and isn't that value to talk about. Whereas with frequency, with your cell phone, with the new iPhone, it'll be 120 seconds. It's 120. What am I trying to say here? 120 cycles per second is what I'm trying to say. Or 120 refreshes per second. So having numbers that increase instead of numbers that get smaller and smaller, that's a common psychological theory that makes you think things are more valuable. So frequency, we get into that as well on this next slide here. I wanted to compare it to period and have it on the last slide so you could see everything. 1 cycle per second is equal to 1 hertz. Again, we said that period, and period is also known as, period is T, which is equal to um, cycles per second. And then frequency, which is this F, which is equal to frequency, is equal to, I have this mixed up here. This should be seconds per cycle. And my apologies. This should be seconds per cycle. And this should be cycles per second. Like such. So, kind of the common example of that is, how often do you get your haircut? Once every 6 weeks. It has been, it's been 2 months for sure. Well, it's been almost 3 months. It's been almost 3 months since I got a haircut. So my hair is looking super long and super gross. I'll have to try and get that resolved before we go back to school. Or maybe I'll just grow it out. It looks really bad. Factors that influence waves. So again, frequency and period, they have an inverse relationship. This statement here is what I just drew on the last slide. So what that means then is that the period is equal to 1 over the frequency, and or the frequency is equal to 1 over the periods. Waves can have the same frequency but different wavelengths. Waves can have the same wavelength but different frequencies is kind of what that means. Yeah. Amplitude. This is the last thing that I want to talk about today. A larger amplitude wave will transport more energy than a smaller amplitude wave in the same medium. It's kind of a confusing sentence, but basically what that means is if this amplitude is higher, like such, that would mean that that wave is carrying more energy than this green wave is. Even though it has the same wavelength, I should draw that maybe a bit more accurately. So even though this has the exact same wavelength, it's carrying less energy because this amplitude, because this amplitude, I want to change where that is so much smaller. So this is a small amplitude. The energy transferred is proportional to the amplitude squared. That's kind of just a confusing way of saying that, like, um, the yeah, I guess it's just kind of a confusing way of saying that, like, as the amplitude increases, the energy also increases. A medium. So again, that's whatever our wave is traveling through. With a lesser density, we'll have a larger amplitude. So again, if like you can think of it like swimming or trying to run in a pool versus trying to run on a sidewalk. Running on a sidewalk's really, really easy because the air isn't providing much resistance. And so you can burn a lot more energy and travel a lot faster. Um, or, yeah, you can run faster. If you're in a pool and you're trying to sprint, you have a lot of density and a lot of resistance against you. And so it makes it really, really hard to run quickly when you're in that swimming pool. And as such, your wavelength or your speed would be a lot slower. That is our intro to waves. Does anyone have any questions about our intro to waves? All right.